I hope that I didn't take a lot from your time. Dr. Adwan, I think if we are ready, I could present Dr. Mohamed. Dr. Mohamed Ismail, are you here? I think Dr. Mohamed is already.
Yeah, hi, Ahmed. I'm here. Yes. Good morning.
So I hold my share, please, and co-host Dr. Mohamed as a co-host. Okay, I will present Dr. Mohamed. Dr. Mohamed Ismail is one of the. Let me, Dr. Mohamed, introduce you, please. Okay.
Make it short, huh?
Thank you. Thanks so much. Okay, please stop my sharing screen. I don't know, is it stopped or not? Yes, yes. Yeah. And if Dr. Mohamed Ismail is a co-host, right? So I could present Dr. Mohamed. Okay. So, so our session, our first keynote speaker today would be Professor Mohamed Ismail. Actually, Professor Mohamed Ismail is one of the professors that are already working in the electronics engineer. He obtained his BSc and MS from Cairo University, Egypt, and the PhD from University of Manitoba, Canada, 1983. He's one of the I think he's the only founder for analog VLSI lab in the Ohio State University, one of the foremost researchers inside mainly in different fields, analog mixed signal and RF circuits, served mainly. And he has also held a research chair at Nano Electronics Circuit at Swedish Royal Institute of Technology, KTH, where he founded a Ramses research group, which is related to radio and mixed integrated system research groups. He has numerous number of publications and patents already I could say around more than 15 patents, US patents mainly. Actually, his talk now would be related to one of his newest projects that already has been working in the research point with Cleveland. I think this is one of the points that I say. He's already in the editorial board of many electronic integrated circuits, or analog signal processing, and also he's in the served as an IEEE mini editorial and administrative capacities, and he's the founder of IEEE International Conference of ICCS and many international conferences. And personally, I could say that Professor Mohamed Ismail for me is like I would say is Ismail, like a king of electronics mainly. The floor is yours, Dr. Ismail, and I think we are all waiting for your talk. Thank you.
Thank you so much, and I really appreciate this very kind introduction. And good morning, everyone. It's a pleasure to be part of this very nice event. I wish that the next time this event would be held physically in Egypt, so that I can come and meet everyone in person. Yeah, my name is Mohamed Ismail. I'm from Wayne State University in Detroit. And I'm very happy to share some of our recent research work that is actually done in cooperation with a team in Abu Dhabi, where I used to be there for a number of years, 6 years. I founded the department there, Ecg department, and I still have a position there, and we have some students, and we have some exchange and between our team here and the team in Abu Dhabi. Okay, so I will, before I get to the technical part, I just want to share some of our experiences here in the US. I think that might be beneficial to the students and in the audience. So let me just go to the next slide here. So, okay, so Wayne State is one of the big universities in Michigan. We have about 28,000 students. It was founded over 150 years ago. Actually, last year we celebrated the 150 years anniversary. And it's a large public school. It has every specialty you can imagine: medicine, dentistry, pharmacy, engineering, arts, physics, you know, you name it. We actually are located in Detroit, downtown Detroit, and we are just across the border from Canada. So we do have about 5,000 students from Canada in the neighboring cities. And they actually pay the same in-state tuition as our students in the US, in the Michigan area. So we have a lot of international students, and we are located, of course, in the automotive capital of the world. We have all the big automotive companies, General Motors, Ford, Chrysler, Mercedes, Toyota. Any company that does automotive worldwide has some activity in Detroit. We have large companies, we have medium and small size companies as well. We have about maybe 2,000 companies and around the Detroit and the Michigan area, also in Ohio, which is a neighboring state. And that actually we benefit from that significantly. I mean, we have a lot of projects with those companies. We have actually a very strong industrial board of advisors. We have a large population of alumni located at leadership positions in these companies. So we work with those companies. We also work with companies elsewhere in the US, especially the semiconductor companies and also the wireless companies like TI, NXP, Intel. Yeah. And so that's, and that actually the reason we have that large industrial interaction. Well, this is just the city of Detroit picture from the Canadian side. We have actually a river, the Detroit River, that separates Detroit from Windsor, in Ontario, in Canada. This is just a small map to show you where we are. Right, this is Lake Erie here, and this is Detroit, and this is Windsor is actually located in Canada. So our department, the Ecg department, which I chair, is the largest department in the College of Engineering. We have, in the average, about 300 students in the undergraduate program. We have computer engineering and electrical engineering. We have about 200 master students on the average and about 60 PhDs. Although we have, this year we have suffered a little bit with having international students because of the COVID-19. However, many of those students actually joined us online, and we charge them in-state tuition because of the fact that they are not here. So we are trying to cope with this situation. Our courses has been online this semester and also next semester as well. Our students started to suffer from what we call Zoom fatigue. So we actually have this Friday coming is a mental health day to cope with this issue. Because people are started getting, you know, tired of this online thing. We have 24 faculty that are full-time, but we have about maybe 10 faculty that come on part-time basis, lecturers, and so forth. We have 5 NSF career awardee. We have now 5 IEEE fellows. Let's see, this is just a picture of, it's a bit old, like maybe a year old or so, showing the professors and the different areas of interest of research. In our strategic plan and also our culture, we put a lot of emphasis on project-based learning and hands-on. You know, it's so important for us to integrate hands-on components into the education. So people like, we have, of course, the capstone design projects that run for 2 semesters, and we get students working from different departments on some exciting projects. So I just wanted to mention that. Okay, so now we go to the introduction. So, okay, so the topic, and I may still do some introduction about the VLSI lab that Ahmed spoke about in the introduction, but the technical chip that I'm going to present today actually is a great example of a chip that has a lot of cross-disciplinary areas, from machine learning and classification to energy harvesting to power management to IoT to SoC. And it's a good example also of having large team of people working together to do some big things, like, you know. So I'm going to introduce this, you know, in a few minutes here. And we even have some graphene-based sensing as well. So it's material science. So the VLSI lab, which I started at Ohio State, still there. In fact, it's now led by one of my former PhD students. Is one of the very famous research labs in the US, focused on analog mixed signal, RF, and SoC. So this lab actually generated so many students in industry, like over, you know, I actually advised about 50 PhDs. And many of them are in Silicon Valley and in Texas, Arizona, and even overseas. So this is just an old picture of the lab here. And we do a reunion every year with the ISSCC in San Francisco, with the alumni of the lab at Silicon Valley. And we meet in the same restaurant every February. But this year, of course, it was actually in March, and we couldn't do it because of the confinement. One course that became very well known, and we still have that course here in Wayne State, is a Vlsi Design course, where students actually do projects. And you can see this is a poster session that we do at the end of the course, where students present their projects. And then all these projects are chip design projects, like designing a PLL or an RF IC receiver for a wireless LAN, and we celebrate at the end of the semester. So the course actually was very populated with so many students, as you can see. Many of these guys that you see in front of you are now in industry in places like TI, Intel, and NXP, other places. Some of our research output spans a lot of areas: radio design, nanometer technologies, RF power amplifiers, multi-standard radios, how to handle substrate noise, you know, and so forth. Now we have the center in Wayne State, which is called WayneCAS, and it stands for Wayne State Center of Excellence in Integrated Circuits and Systems. And here is a website. You can take a look at the center if you have a chance. And this is a team right now. We have 2 professors and myself, and we have 10 PhDs and 1 postdoc. We have a number of master students and also undergraduate students doing research as well. We have these type of projects. I'm going to actually send this presentation to Dr. Ahmed, and then you can share it with whoever wants to take a look. We have a lot of different equipment to do characterization, and also software tools, cadence, synopsis, mental graphics, ANSYS, and so forth. These are some of the things that we have done recently over the last 10, 15 years. One of them actually was part of a startup a company that I started in Stockholm, in Sweden. And that was one of the first CMOS transceivers for wireless LAN, and covers like 802.11 ABG. And it was actually sold to a company. And this is the chip that I'm going to talk about today, which is a self-powered biomedical processor that actually predicts the onset of a heart attack before it happens. And we are in the process of commercializing this work. In fact, I was very pleased. When I joined a bit, maybe 20, 25 minutes before my talk, and I listened to the lady talking about innovation and entrepreneurship. And in fact, I was very pleased that this activity is Nile University is doing this, because it's now considered one KPI performance indicator of success of research is to try to impact the economic environment, create jobs, and basically commercialize the research. So I hope that to see more of those activities in Egypt in general. So, okay. So now we start the, and this would actually be very interesting to the students because this is a building block of the chip that I'm going to talk about today. So we have here some kind of energy harvesting blocks. Of course, when you harvest energy, you harvest a very small voltage or current. So you have to actually do some kind of power management to make that voltage in the range that can actually power up different parts of the chip, like 1 volt or 1.5 or whatever. So it comes out of this is a voltage that actually powered up different parts. And the first part to the left is a sensor, you know, and that actually is a very good example of an IoT edge unit. So you have sensing, you have processing, and then you have transmission or communication. So these are the three main basic operations of an IoT block, is that you have to sense a phenomena. And of course, that phenomena is normally an analog phenomena from the physical environment, like it could be temperature or speech or an image or anything in the physical world. So you have to convert it to digital, and then you have to process it in some kind of a DSP with a certain algorithm that is implemented in that DSP, and then you take it back to the analog world with a DAC, D2A, and then you transmit it through some means. It could be wireless or wireline, or, you know, that's basically the. So all these different things are actually in the chip here. I'm going to talk about that more in details, but and now you will be able to see this graph a few times. That chip actually received a lot of attention. It was done in cooperation with the team in Abu Dhabi. It received actually it's a world first CMOS chip that predicts the heart attack before it happens. So our vision when we developed this thing is that the patient can actually have it implanted or wearable device that would actually detect that something is wrong, and then would send a message using the mobile phone or some kind of a Wi-Fi device, depending on the environment, to the point of care, you know, in a hospital or in a. And we are working with Cleveland Clinic in both in Abu Dhabi and here in Cleveland, Ohio, to get. We are in the process right now, actually, of verifying this on real patients, and actually in the first phases of this research, we obtained the database from the American Heart Association. Basically, all you need is an ECG signal to put it into the chip, and the chip will take care of the rest. You know, it will basically determine if that ECG signal is that of a person who is a candidate to have a heart attack, or he is not. So I'm going to, and the accuracy of this was 99%. Okay, so we also had a data set from the MIT PhysioNet. This was actually, we took it for free, but for the American Heart Association, we had to pay for the data set. Okay, so as you probably know, of course, that there's so many devices right now that's under the name IoT. 2023, the market for IoT devices will reach about $35 billion US. And okay, so this is a block diagram, as I mentioned earlier. You have sensing, you have processing, and you have communication. And this is basically the power line, which basically either most of these devices, of course, are because of the fact that they are wearable devices, so they try to avoid using battery. So you can use some kind of an energy harvesting mechanism, either RF energy harvesting or some kind of thermoelectric energy harvesting or vibration, or there are so many different kinds. And you'll see in the literature actually so many papers discussing how to harvest energy to avoid having to use battery, especially if you have an implant, something that's implanted that you don't need to take it out every once in a while, every few years to change the battery. So, okay, so we looked at the so-called ventricular arrhythmia, which is the name for heart attack. Of course, this is the first cause of death in the US and elsewhere for men and women. And the motivation, of course, is that there is a lack of continuous monitoring of patients. There is a high population growth, and there is rapid enhancement in the sensor technology. So we feel that technology can actually help us to better monitor people on the go. They don't have to be tied to a bed, or they could be walking around or driving or wherever they are. We can still monitor them, and we can actually also know what's happening with them. So we started thinking about this device, whether we can have it wearable as a watch. And of course, as a watch, then you can have it in your hand. You can harvest the energy of vibration of the hand. You can also harvest the thermoelectric, you know, the body heat. Okay, so we can actually get this thermoelectric generator on the shelf. It's very cheap. You can buy it, and it actually tests. It basically takes the difference between your temperature and the temperature, the ambient temperature, and convert that to volt. I'm going to show you that in a second. We also talked about having something around the you know, some kind of a headset, but then we basically abandoned all that, and we came up with this nice kind of that you can look at it as a piece of jewelry, for example, that you have here the Ecg Electrodes, that you can wear it as a necklace. So these will sense your ECG signal. This is your harvester, which is a TEG, thermoelectric generator, and this is all the electronics that I'm going to show you in a little bit here. Very small, 3 centimeter by 3 centimeter TEG. And yeah, so if you compare that, for example, to what they call a Holter, that people actually use to monitor the ECG overnight, it's a much more smaller device. And we're actually figuring out the sale price for this to be around $75. It costs about maybe no more than $5 to produce it. Of course, that depends on the volume. You have to have it in very large volume to reduce the cost. That's the economics of microchips. Okay, so that's again the same slide that I showed you earlier. This each of these blocks actually was a project, you know. So I mean, we have a large team of people. So some people were working on the energy harvesting and power management. Some were working on the sensing. We started in the first generation using MEMS, but then we switched to using graphene. And I'm going to show you some results. And then this is the front end. This is the DSP part, and this is a wireless transmitter that transmits the result to a remote location. So the first part is the sensor, and as I pointed out just a moment ago, that we used the graphene. This was a different group working with materials, and we were able to actually do this patch, you know, material that made from graphene powder. You can see here, and we were able to do this type of patch, you know, here, that is basically primarily made of fabric and graphene, and we actually put it through the washing machine to make sure that it's still robust. It's not going to get affected by water or anything like that. And then we used it to sense. This is how the fabric looks like. We used it to sense the ECG signal. And because the graphene is very highly conductive material, we were very pleasantly surprised to see that the ECG signal, we compared it with the conventional way of taking the ECG signal, which basically, you know, you put these things around your body, and it gets sticky. It's kind of invasive. And we were able to see that with graphene, it was much less noisy, and we also have a very high signal level compared to the signal level that we get from the conventional way. And we did it again just to make sure, and we found out that it really performs very, very well. It's very highly sensitive, less noisy, and provide you with a very reasonable signal level amplitude. Then we, of course, all the devices that are out there that basically does detection of the ECG signal. But what distinguishes our device is that it does prediction of what can happen, you know. So it's extremely important for preventive medicine, that if you can find out if you have a problem before it happens. So we actually look, everybody else looks here after the heart attack happens, but we actually look here, look in the back, you know, before the onset of the heart attack. So, all right. So, and our vision basically was to, as I pointed out earlier, is to have everything done locally here, like the signal acquisition, the processing, and the analysis is all done in the device. And the result of this analysis is sent to the nurse or the doctor at a remote point of care. Again, this is the same picture that I showed you before. So we have thermal energy harvesting that I'm going to show you. We have power management unit. We have the sensor here, and we have the processor and the communication. All this was done on the same. The only thing that was outside the chip was the energy harvesting device, which is the thermoelectric device, and the graphene-based sensor. Everything else was integrated. So I'm just going to skip this one. I'm just trying to make this presentation at a basic level, tutorial level, without getting into too much equations or to make it more easy to follow. So the novelty, there's some, so some of the things that we did were improvement on some previous work, and some of them were totally new, like the feature extraction, the TMP wave delineation, and the machine learning, of course, and classification algorithm. So the main innovation here actually is we were able to do a lot of random statistical signal processing on the ECG, and we were able to unveil or find out that there are certain features in the ECG signal that actually distinguish between someone who is a candidate for a heart attack or is a normal person. And these features, which were extracted, are basically 7 features, and they are time domain sets that basically are taken as a time difference between 2 consecutive heartbeats. Like this is a heartbeat and this is a second heartbeat. So you have all these time periods, which are basically 7 of them. And it turns out that these features, if you do like some classification, I'm not going to, as I said earlier, go to these things, but it turns out that if you let me just go back here. If you do analysis on those 7 features, you'll be able to show if one set of those 7 features belong to a normal person or they belong to someone who is a candidate for a heart attack. So we were able first to do a chip and I would like to always show the first generation of those chips because we have so many of those. We put that in a chip and tested it in the lab. And this is actually the result of the of this. So you put the ECG signal in, and then to the SoC setup, and then the SoC setup will analyze the signal and then give you the output. So this is the input ECG, and then you have the features coming out, the 7 features that I spoke about earlier. So it was actually a very nice way to, and we actually used an in-house processor. We didn't use like an ARM or it was a lightweight, low power DSP processor that was actually built by ourselves. Now we go to, so this is one aspect. So far we have 2 aspects. We have the sensor, the graphene based, we have the processor. Now we go to the energy harvesting part. Of course, the energy harvesting depends on the source that you are harvesting. If you are harvesting, like say vibration, that's AC. So you need to actually rectify. If you harvest an RF, that's an AC, but if you harvest thermal energy, that's DC. So each of these different sources will have different way of circuitry to handle them. Okay. For example, if you have an AC RF, then you have to convert it to DC first, and then you do voltage regulation, and then you eventually, you know, with power management, you can generate the 1 volt or so that you need to use to power up the chip. Okay. Excuse me. I don't know why it doesn't. Okay, here it is. So let me just skip that. So this is actually the thermal energy harvesting device that you can actually buy on the market. It was like a few dollars. So you take the temperature difference between your body and when you put it on yourself, it takes the difference between your body temperature and the outside temperature, multiply it by a constant, which we call Seebeck effect, and then give you a voltage here, VT. Okay. So like I said, this device is available out there in the market. You can buy it, and it gives you like somewhere between 24 millivolt and about 20 microwatt power. This is what we have seen in the lab, but in the catalog, this is what they say. So you always have to measure it to make sure that you have the correct number. So this TEG will generate this type of a volt. And then you need to actually make sure that that volt is good enough to power up the device. You have to use some kind of a DC to DC converter. And there are different ways to do that. One of them is the LDO, or some of you know power management, but unfortunately this doesn't work because this device, this voltage here is so small to turn on a MOS transistor. The VT, of course, is about 400 or 300 millivolt. So, so that's not going to work. There are several ways of doing this. You know, the conversion. What I mean by this is the DC to DC converter. So what we ended up using actually is, of course, there's a switch capacitor converter, which basically uses switches that are MOS transistors and capacitors. But what we ended up using is this one, because actually it has a very high efficiency. It's very scalable. But the only problem with it is that it uses an inductor, and that inductor is very large and cannot be integrated. So you have to put it off chip. And the way this thing works is that you take the voltage from the TEG, from the harvested voltage, and that voltage will generate a current. This transistor will be on. So the current will charge this voltage, VD, to a large value, to a reasonable value. Then this one will go off, and this device will go on. And then the voltage here will start to charge this capacitor here. And the voltage across this cab can be much larger than this one by the ratio of the width over length ratio of these 2 transistors here. W over L of this device divided by the W over L of this device can give you like maybe 1,000 times. So if you are in a microvolt range, you can get to a millivolt and so on. So this is actually how this thing works. The only problem is, as I said, is that inductor here is The other problem is that this voltage has to always be positive, meaning that the TEG has to generate a positive voltage, right? And if it generates negative voltage, then we might have a problem, but we have a solution to this one, to this problem. What I mean by, okay, let me go back. What I mean by that is that if this voltage here, of course, this voltage here basically is the difference between your body temperature and the outside temperature. So if you are like in the south part of the earth where it's hot, or if you are in the summertime, then you might have a positive voltage because the temperature outside will be higher than the 37 degrees. But if you are in the winter times or in the north, Sweden, Norway, or some of these countries, then it will be negative. Okay, so we need to find a solution. How can we make sure that that voltage always remain positive for this circuit to work? So we go back here. So this is actually more of a detailed operation of the circuit. So this is a current that goes in here. This transistor switches stays on, and this one is off. This voltage here starts to rise. And when this one goes off and this one goes on, then the voltage will charge this capacitor here. And these are the two clocks. One of them is clock 1 and clock 2. There's some kind of a zero current switching, because in that zero current switching, the function of this one is to make sure that this thing is very highly efficient, because if things are not working well, you might have an instance where the current actually can go the other way, and that will reduce the efficiency. So in order to minimize this from happening, we developed some kind of a zero current switching circuit that I'm not going to talk about here just to save time. That actually, with this circuit, we were able to raise the efficiency from 79 to 90% of this device. You know, without getting into how actually this thing settles. I mean, there's so many issues that I will take time to explain. We also tested this, actually this chip sits here, but this is actually the actual size of the chip. All this work was, by the way, was done in Global Foundry, 65 nanometer CMOS. And we are now working with TSMC, and we are trying to put this in 22 nanometer. So yeah, the polarity issue that I mentioned earlier, if this thing is positive, then there is no problem, you know. But it actually could be negative. So how can we actually deal with this situation? So in order to deal with this, we have to, first of all, we have to monitor the polarity of this signal here, whether it's positive or negative. And based on that monitoring, we can actually have a very simple matrix made of transistors that can actually switch things around to make sure that what you end up here is positive all the time, okay? So, okay, so how did we do that? It was actually a very simple way. By the way, this issue is done by other companies using transformers, you know, and of course the transformers don't lend themselves to integration. So while this is the only solution actually that I'm going to show you that lend itself to integration, and many of these pieces, by the way, I forgot to mention, they are patented, you know, including this this technique, the auto polarity control. So okay, so let's say that the voltage is positive here. In the charging phase, you have this device on, and the current will go this way, and this device is off. Okay. When you have a discharge, excuse me, then this device will go off, and this one will be on, and that's what you have here. So we notice that that voltage here, VD, is a very critical voltage, because actually, when this voltage is positive, this node rises to V storage, which is a capacitor voltage here, plus this diode connected device. So you have a V store plus V threshold at VD. So this is in when the voltage is positive. Now, when the voltage is negative, you can see the negative Now the polarity is negative, and the current will actually go this way instead. Okay. In the first phase, this device is on and this one is off. And then this is the charging phase, and the discharging. It turns out that when this one is off, you have that voltage here, which is a diode voltage, which is negative. Okay. So using the polarity of this VD, you can monitor whether the input is positive or negative. Okay, so what you really need to do is to compare VD to 0. So using a very simple comparator, we'll compare VD to 0, and based on that comparison, you can actually have a control that can control the switch matrix that I spoke about before. So you can go like this, for example. So this is a switch matrix here. You have 4 MOS transistors. You have so if this voltage is positive, then you can enable this device and this device to be on, and this one will be off. So you have this picture here, for example. But if that voltage is negative, then you do the opposite. So you actually enable these devices. You can have this positive will go here, and that negative will go to the ground. So you always have positive voltage here at the input. Okay. So you can just do a finite state machine for this to implement it, and then we implemented that, and that actually shows you here that this is your VTEG, could be positive or negative. In both cases, you have, this is a VD, which actually, this is a zoom in of the, when VTEG is positive, you have this, which basically is zoomed in here. When it goes negative, then you have this negative voltage here. So this is the differentiation between the two. V-store will stay the same, and these are the clock. And of course, you have to monitor that every once in a while. In our case, we monitor it every 1 millisecond. Okay, we tested that again in the lab, and it was the normal polarity and was the reverse polarity. And then we compare this to other techniques, and most of those techniques are using transformers. Some of them are published. So just to, I'm almost done here. I know that I might be a bit running out of time, but so of course, as I said earlier, this is a task. All these different blocks are different tasks, like, you know, by different. So we have a large team of researchers that did this project. We had a project manager that actually was able to combine and do debugging and do system integration. You know, these are all skills that are very important in industry. And okay, so this is actually the very first generation of the project, where everything was integrated here. And the front end was not at that time integrated, which has the ADC. And this is a radio, which is it was basically a 120 gigahertz on-off keying transmitter. And this is the Ecg Electrodes, which were graphene based. So as you can see in this, everything that basically was on, you know, on chip, the energy harvesting, the regulators, the power manager, the Ecg processor, which is the digital part, the radio, the front end. This is a graphene based Ecg Electrodes, and this is a TEG energy harvester. This is how the chip looks like, the first generation, which was 65 nanometer CMOS global foundry. Some of the papers that, for the students who are interested to read the bits and pieces of this work, they can actually follow some of these papers. One of them was the best paper award for the transaction VLSI. It was the best paper published in the 2017, I think. And we have also a few patents that. In conclusion, I just introduced the first self-powered SoC for a signal processor for the ECG, and the sensor is graphene based, and it's the first device that predicts the heart attack before it happens. The reason we say 3 hours here before it happens, because the American Heart Association database that we have received basically goes back 3 hours before a heart attack. Now we have this data set from the Cleveland Clinic that we are testing to see how long actually this thing, you know, it's not, we believe that this is something that works for several weeks, not just 3 hours. So I mentioned, when I did I didn't mention the classification that we used for the machine learning. It was naive Bayes classifier, first order classifier. The reason we chose that is that it's very easy to build in hardware, it's low power, and it doesn't take much space. And we, on top of that, also, in order to eliminate any piracy of the chip, we have implemented a layer of hardware security on top of the chip. I did not present this here today, but we had a paper actually published last year, a full-length paper that discuss how we implemented this hardware security on top of the chip. So as I said, it was 65 nanometer. This is the power consumption area, very small, the volt, the frequency, and the accuracy. So we are looking at human sensors of blood pressure, the ECG, the oxygen level, you know. So we're looking into, in fact, we are almost done with this EEG, something similar to what I just presented. And we're doing this EEG in collaboration with some doctors in the Wayne State Medical School. This is some of the people from the Abu Dhabi side that did work on this project. And I would like to thank them again. And I would like to also thank my role models, Gordon Moore of Intel and Carver Mead of Caltech. Thank you so much. And if you have any questions, I'll be happy to.
Thank you, Professor Ismail, for this nice talk. Actually, I enjoyed it a lot. And I think we have time for questions. If any have a question, please, participant, please raise your hand. And the coordinator of the session will open the floor for questions.
I have one question, Dr. Ahmed.
Yeah, sure, Dr. Tariq.
Thank you, Dr. Mohamed, for the very wonderful piece of research. I really enjoyed this. It's
thank you so much. Thank you.
It's really very nice. I was just going to ask you, you mentioned that you are about to commercialize this. How are you going about that in terms of the university rules as well as how you can do it on?
Yeah, actually, we have one of our main investigators who's actually on leave right now because you cannot do this while you are in the university. Because the most important thing is what we call conflict of interest. So we want to make sure that the company doesn't use any of the tools in the university, and then they have to be completely independent. We did some round of financing. We started with an SBIR from NSF, and now we are getting some funding from some venture capitalists. So we're in the process of closing one round of financing right now. And I know what you mentioned here is, your question is very important because we, when I was in Abu Dhabi, I noticed that the culture of startup needed to be created. You know, here in the US, if you start a company and fail, people still think that you have done something great. But in other countries, unfortunately, this culture is not there yet. So I hope that Egypt, people are encouraged to start companies without fearing of having to fail, because actually the failure rate is very high. I mean, you're talking about maybe if you have like it's less than 10%, you know, the success rate. So most of the startup companies actually don't make it, and the companies that make it are very few. It takes a lot of different. You have to have a good management team. You have to have good value. You have to actually work with some kind of someone who can actually do some due diligence to make sure that you have the patents, you have that you did the literature search, that you have the strong technical team that can, so based on these things, and then of course you do market landscape, competitive landscape, you do the so-called SWOT analysis, opportunity, I mean, strength, weakness, opportunity, and threat, which is called SWOT analysis. So you do all these things before you actually speak to VCs, and it takes a lot of time. Unfortunately, because of the COVID-19, we were delayed quite a bit. I mean, and we're still struggling with this issue here in the US. So, but so I hope I answered your question. I don't know if you want to.
Yes, you have. We are trying to establish this culture very much. I mean, we are working very hard on this here at NILES University.
Yeah, I noticed, and I was very happy to see that actually. And I really wish you the best and of success in this regard. I mean, it's here in the US, and I'm sure that in other places, they measure the success of research now. One of the key factors is this research going to impact the economic environment, and does it lead to, it's not just publishing some papers or getting some books or whatever. I mean, does it actually create jobs? Does it build new products? You know, that sort of thing. So it's becoming much more important now, and I was very happy when I heard the presentation from the lady.
Yes, this is part of culture of NILES University actually. That
very good, very good.
And promote throughout Egypt actually.
Sure. Yeah, that's very good. Any other questions?
Any other questions?
We're looking for PhD students as well. If you would be interested to join, you can just send me an email. Master or PhD students.
So sure. Professor Ismail, I think as I see, I didn't get questions because usually your talk is so illustrative. So I think no one has a problems with that. Actually, I want to thank you again, Professor Ismail, for this nice talk, and also for waking you up. I think it's earlier now than you wake normally. Yeah, sorry, but you know. But we already enjoyed so much actually for this talk, and I hope that we could see you in Egypt in NILES University as soon, inshallah, in NESC. We will wait for your visit, inshallah.
I will be happy to do that, and thank you again for inviting me.
Thank you, Professor Ismail, and thanks for this nice talk. And I will talk to participants. Please, after this keynote speaker, we will have a short break, and then we'll have 4 running sessions: SA1, SA2, SA3, SA4. Please go to the program sent you by PDF. The PDF sent to you by email, so you can access your right session and be there in the right time, please. And if you are a presenter, don't forget to name yourself with the ID followed by your full name. Okay? So I think we are done with this session. Thank you, Professor Ismail, for
thank you so much.
This nice session, and wish to see you soon, inshallah, in Egypt.
Inshallah.
Thanks a lot. Thanks.
Bye-bye.
So this ends our session. Okay. Professor Radwan is here.
Thank you, Professor Mohammed, and thank you, Professor Ahmed Madian, for this nice presentation. And now we have 4 panel sessions. Thank you again for participating in NILES 2020, and wish you success, presentations, and fruitful discussion, inshallah. Thank you very much. This is the end of the first session. for the opening and the first keynote speaker. Thank you very much.